Good afternoon, everyone. As we know, the rapid progress of urbanization has modernized many people's life, but also generated a lot of issues: traffic congestion, air pollution, and energy consumption. Tackling this challenge seems nearly impossible years ago, given the complex setting of the city. But recently, the advances in sensing technology and large-scale computing infrastructure have generated a diversity of big data, from social media to traffic data, from map data to meteorological data. When used correctly, we can solve the problem we are facing in city by using this data organically. Motivated by this opportunity, we come up with a vision on urban computing, which connects urban sensing, urban data management, urban data analytics, and service providing into a loop for recurrent and unobtrusive improvement on people's life, city operating system, and the environment. So clearly, this is a multiple data source, multiple task framework, where we have a diversity of data and a variety of tasks. In the meantime, even in one task, we have to harness a diversity of data. Let's say, if we want to improve urban planning, we have to look at the traffic data, map data, even the population data. So how to unlock the power of knowledge from data across different domains is an essential thing of big data. And this differentiates between traditional data mining and big data. And today I will focus on this topic. That is how to fusion the data, how to unlock the power of knowledge from data across different domains. So we started this research theme since 2008. We have done a series of technical work from urban planning to transportation and to environment. And today, I will use 3 concrete examples to demonstrate how we really aggregate different domains data to inform people's decision making. The first one is about air quality. Now it's a global concern, especially in developing countries like China. Many cities have built on the ground air quality monitoring stations to inform people their ambient air quality every hour. However, the number of such kind of monitoring stations is very limited because building such kind of station is very expensive in terms of land use and human money and human resource for maintenance and deployment. Unfortunately, air quality varies by location significantly and is highly skewed in the city. So this figure shows a replay of the historic data in Beijing, where each icon stands for an air quality monitoring station that has been built by government. The number associated with each icon means air quality index. The smaller, the better, the bigger, the worse. Green means very good, red means very unhealthy air quality. As we can see, even at the same moment, the air quality reading from the 22 stations in urban area of Beijing can be dramatically different, even if they are only a few blocks away. It's not surprising to see this phenomenon, because air quality is influenced by multiple complex factors, such as traffic flow, land use, density of building, and even fine-grained meteorological data. And this data can be very different in different parts of cities. Now the problem is, we don't really know the air quality of a location without a station. What's the air quality of our current location if there's no station built? So we cannot use linear interpolation to calculate air quality because it's non-linear. We cannot use average reading from station to represent the air quality of our current location. So what do we do here? We infer the real-time and fine-grained air quality throughout the entire city by using 2 parts of big data. The first part of data is historic and real-time air quality data from existing monitoring stations. The second part of data are 5 additional data sources we observe in the city. Meteorological data, such as windy, humidity, temperature, etc. Traffic flow data, what's the travel speed of vehicles in this particular area. Human mobility data, the number of people departing from a region and entering a region. Point of interest data, How many restaurants are there? How many movie theaters? How many factories are there? What's the density of POI in a particular region? Road network data. How many intersections, traffic lights? What's the length of highway and what's the length of service road in a particular region? Using data mining and machine learning algorithm, we can build a network between the data we observe in the location and the air quality of the location. In the future, given the data of a location, we can infer its air quality even if there's no station built there. So as a result, we can achieve 1 kilometer by 1 kilometer fine-grained air quality throughout the entire city. What this kind of fine-grained information can do, it can really inform people's decision-making. We know where and when we should go jogging, when should we close our window. And it's also a step towards identify the root cause of air pollution in the future. And you might wonder how we can evaluate your algorithm, your service. We have deployed our service in over 20 cities in China and evaluate based on data of past 1 year. So here's how we evaluate it. So here each blue point means a station that has been built by government. We know its reading. Now we can remove this station from the map, supposing we have no idea of the air quality in this particular place. Then we can calculate the air quality of this location based on our algorithm, and later use the reading from the station as a ground truth to measure the accuracy of our measure. So as a result, we can achieve 80%, more than 80% accurate in Beijing. And what does 80% accurate mean? If using traditional classic model in environmental theory, Gaussian dispersion, I was told they can only achieve 60% accurate at the most. So that means 20% jump by big data. So that's the value, real value of big data. Okay, so we have paper here, but we have a system real working in the real world. So if you are using Windows Phone, you can search for urban air. Then you can check air quality of any location by just clicking on a map. We also have a public website demonstrating this service, covering 20 cities in China. And it's also transferred into BMAP and the Chinese Ministry of Environmental Protection. And this technology has been used during the APEC 2014, which was just here in Beijing, I think in November. So let me show you how this website works in MEP. Okay. So we can check any location by just clicking on the map. I can tell you what's the concentration of air pollution, NO1, NO2, PM2.5 there. And we can see the fine-grained air quality throughout the entire city. And recently, we put together the data from different cities, about 200 monitoring station data, and we can diagnose large region air pollution. By replaying this data of past 24 hours, we can see how air pollutants was blown from one place to another places. Then we can track the source of air pollutions. And given the data of a long period of time, we can see where is the worst place in Beijing in terms of air quality. This map shows the top 200 worst places in Beijing at this particular time of day. And as we can see, when time goes to afternoon, the majority of worst place was located in south part of Beijing, which might indicate the air pollutants may be blown from Hebei province, which is located in south part of Beijing. And recently, we have extended our capability to forecast the air quality at the next 48 hours. I want to emphasize this is a fine-grained forecast. It's not generally saying it's good or not tomorrow. We can forecast for each particular monitoring station at next 48 hours. More specifically, in the next 6 hours, we can predict a value for each hour. You can see. And for the next 7 to 12, 12 to 24, 24 to 48 hours, we can provide a range, that means max min air quality of this particular time slot. So having this kind of information, we can really inform government decision making. So for example, during APEC, whether we should close more factories, okay, this prediction has been considered as a factor to make their decision to close or not factory in a farther distance to Beijing. So we'll save millions of dollars per day for government. The second example is about New York City, about noise, which was derived from Cars, directed by Steve Cooney. So New York City is a city jungle with a mixture of multiple sound sources, traffic, construction, loud music. Urban noise does not only compromise working efficiency, but also impair people's health, mental health, and physical health in the long run. To tackle urban noise, we have to model the city's urban noise. But this is not easy at all, given the following three reasons. First, noise disappears in seconds. This sound disappears in a few seconds. And the noise situation of our current location might be very different from the location that is only 100 meters away from us. So if we are going to use sensor to monitor the fine-grained noise situation in the city, we have to deploy one sensor in 100 square meters or even fine-grained location throughout the entire city. That means New York could need millions of sensors, which is infeasible. The second reason is even more important. The measurement of noise pollution does not only depend on noise level measured by dB, but also people's tolerance and feeling about noise. The latter change over time. For instance, I'm talking like this, which will not be considered as noise right now, but if I keep on talking like this during night when you're going to sleep, you will consider this is a bad noise. So that means a quiet noise will be considered heavy noise pollution during night. And the sensor data cannot tell us people's feeling and tolerance about this part of information. The third reason is even more important. The urban noise is a mixture of multiple kinds of sound source. We have to tell government, for instance, at this particular location, during morning, 80% of noise was generated by traffic, 10% was derived from loud music, and 10% was derived from construction. Only knowing such kind of composition of noise in a location, government can make some policy to change the situation. Otherwise, they can do nothing. So it sounds impossible to solve this problem by using sensor data. But fortunately, we have additional data source. That's the 311 data just mentioned by the ministry. In New York City, probably you know 911, that's for emergency. 311 is a platform that allows people to complain about what they feel annoyed by, but without being an emergency. So when making a complaint, you have to provide the location, time, and the category of a complaint. So this figure shows people's complaint on noise category. Well, the height means the number of 311 call about noise in this particular location. And different colors stand for different categories of noise, such as noise about construction, noise about loud music. This is actually a data as a result of human as a sensor and cloud sensing. That's what I'm talking about. Human as a sensor and cloud sensing is quite a popular concept and technology in urban sensing to collect data. This data is very good to reflect on the noise situation of the city. Why did I say that? Okay, the more 311 call that have been made by people in a particular region, the more noisy this place could be. Second, the distribution of 311 call that have been made by people across different noise category could stand for the composition of noise in this location. Let's say if we receive 100 311 complaint call about noise, among which 50 are about construction, 20 are about traffic, and 30 about loud music, then the composition of noise in this location could be traffic versus construction versus loud music in 5 versus 3 versus 2. This is a pretty good result, but it's not good at all. Why did I say that? It's good, it's not good at all. Because conceptually it's good, but the data is very sparse. Some people tell me this is garbage data. This data has been exist for a while. If we only use this single data source, we cannot solve this problem. But we can combine this data source with data from different domains. That's what I can to emphasize. So we combine the 311 data with 3 additional data sources. They are road network data, point of interest data, and the social media data. When put them together, we can infer fan degree, okay, fan degree of noise situation, or say fan grain noise indicator for each region at each time and on each noise category. Why the three data sources are relevant? Let me give you some examples. A region with a denser road network could embrace highway traffic, therefore has a high probability of generating traffic noise. A region with a lot of restaurant bars could have more probability of generating loud music. And check-in data is kind of human mobility data. If there are not a lot of people, people actually are source of noise. So if there are not a lot of people, the probability of hearing loud talking and TV, television, loud and party is actually higher than other places. So having this fine-grained noise indicator for each region, then we can rank the region according to the indicator, and also we can calculate the composition of each region. So let me give you some real system. This system has been deployed on cloud, Microsoft Azure service. So we can check noise situation in the city. Where the deep color is, the more uncomfortable people feel annoyed by noise. And we can replay the noise situation of the city around time of day and check the top 5 worst location in terms of noise pollution in the city. And we can see the composition of noise changing over time of day for these particular regions. So that means we can see why it is noisy. And overall, loud music and party is the #1 source of noise in New York City. And this is true for both workday and weekends. And let's say in terms of loud music, where is the worst place in New York City? It turned out Columbia University is the worst place. Yeah. We overlap the point of interest data on map of the noise map. Okay, so we can see there are a lot of points of interest in category of entertainment and restaurant. So students hang out after classes are there. So in terms of construction, where is the worst place? Wall Street. Wall Street is the worst place. Since the 911, yeah, they're rebuilding something. So, and later we can compare different regions in terms of the composition of noise. We can compare Wall Street with Columbia University, with Riverside Park. You will see the difference. For the, is there? Oh, sorry. Okay, for the Wall Street, construction is the biggest noise source. But for the rest of 2 places, loud music are the major source. So having this kind of information, government can really make policy, make decision, can tackle the challenge of noise pollution. For instance, if we know the major source of this particular location was derived from traffic, we can build some noise barrier along street. If we know the major reason may be the bar, we can do some policy control to control the operating time of bars. And this can further enable interrelay or interdisciplinary research. We can interrelate noise data with hair scale data and see how people's hair was impacted by noise. And third example is about environment, about energy, and about urban planning. So let me ask you 2 questions before step into this example. How many liters of gas has been consumed by the vehicles in the entire Singapore in the past 1 hour? This is a very difficult question to answer. It sounds like a Microsoft interview problem. So the second question is also related. So what's the volume of PM 2.5 was generated accordingly? So government are eager to know these answers. So here what we do, we can estimate the gas consumption and vehicle emission throughout the entire city on any road segment and in the past 10 minutes. I have to emphasize, this is a citywide estimation, not only for a single road segment. Second, we do it instantly. Given the data of past 10 minutes, I tell you the result in minutes, in 1 or 2 minutes. What's the input of the system? We use the GPS trajectory of a sample of vehicles. And fortunately, we have taxi cab running in Beijing. Of course, it's in major city of China. They already have this kind of infrastructure. So we use the trajectory data from taxi cab and combine this data with point of interest data, with road network data, and the weather condition data. Now we can achieve that. Let me show you the real example, okay? This is a result. This figure shows a geographic distribution of gas consumption throughout the entire city, where the red line means high gas consumption road segment, and green means low gas consumption road segment. And this chart shows the total volume of gas consumption consumed by vehicles at this particular time slot throughout the entire city. And the right part of the figure shows the top 3 high energy consumption road segments distributed over the city. And that's the total volume of the top 3 energy consumption road segments. So knowing this kind of information, we can not only know where is the best route in terms of gas consumption, but also we can know where gas has been wasted significantly in some particular region. Maybe this is caused by design, by urban planning design, okay? And more important, we can see what's the emission. Here I show the CO1 carbon monoxide, but we can show PM 2.5, PM 10, etc. So you can see the left part of the figure shows the vehicle emission in carbon monoxide throughout the entire city changing over time, and the red line means high consumption or high emission road segment, and this one means the total emission of carbon monoxide. So that means we have a more accurate way to calculate carbon dioxide, carbon monoxide emission. And we can also interrelate the emission data from vehicles and the reading from air quality monitoring stations. Then we could figure out what's the percentage of PM 2.5 was generated by vehicles. And then government can make real decisions whether we should do traffic control to lower down the air pollutions. For sometimes, maybe in a particular region, it was caused by air pollution, pollution was caused by traffic congestion. But in other regions of the city, it's good. It has nothing to do with traffic. So maybe we can only do traffic control at a particular region in a particular time slot. This will give people more convenience in their life. Okay, so today I talk about 3 examples. I didn't mention how we solve it, but they share something behind. That is how we can unlock the power of data, power of knowledge from data across different domains. It's a 2-part of information. First, the fusion of data. Second, the fusion of algorithm. More specifically, we have to choose relevant data. Putting irrelevant data into a model does not only waste computing resource, but also compromise the performance of model. And second, we have to treat different data sources differently. Some data are spatially static. Some data are temporally dynamic. Putting static data with dynamic data, we are wasting data source. Because, for instance, okay, the structure of road network around this building does not change over time, but the traffic flow changes over time. So if we put traffic data with road network data directly and treat them equally, the road network data would be ignored by the model because it has nothing to do with air quality data, no matter what kind of air quality is. The structure of road network around this building does not change. So we have to use the data correctly, feed them into the right model. And second, on the other hand, we have to understand the merit of each kind of model, organize them organically. Some models are very good at labeling, modeling sequentially labeling problems. Some are very good at doing nonlinear interpolation. So we have to use data correctly, use the model correctly, and organize them organically. So let me revisit big data. We heard a lot of things about big data in past 1.5 days. Here's my point of view, according to my experience in the past 10 years dealing with big data, 9 years dealing with big data. So big data is not a single data source, which is very big. Big data is about data across different domains. Big data does not mean 4 data sets. What we can obtain is usually a part of data, a sample of data. For instance, we can have a GPS trajectory of a taxi cab, which is only a sample of vehicles traveling through the entire city. We should have the capability to recover the true distribution of the vehicles through the sample data. Okay. Big data does not mean dense data. Usually we are facing data sparsity problem like 311 data, like air quality data. We only have a few data in some location, but we don't really have data anywhere. We should have the capability to recover the data through the limited data source. And people said, using big data, we don't really need to know domain knowledge. Yes, probably we need to know less, I say less knowledge. But we need more knowledge about the data and the data science. Maybe people might think the technology is ready. Everything has been done in the data science. I tell you, it's not really true. We have facing new challenge because of the variety of data, because of data across different domains. There's many problems still remains open. Okay, so big data needs comprehensive capabilities to deliver end-to-end service. It's an aggregation of different kind of skills from data sensing, data management, data analytics, machine learning, and visualization. So it's a comprehensive skills. So let me summarize my talk in very short term. I talk about a lot of things about urban computing, but if somebody come to you, ask you what's urban computing, then you just tell him 3 characters. The first thing is our vision is 3B, big data, big city, big challenge. Our methodology are 3M, that's data management, data mining, and machine learning. Our results are 3W, that's win-win-win situation among people, city, and environment. In a shorter code, that's 3BMW. That's urban computing. Thank you for your attention.
Cities and for the people. Dr. Zheng has suggested that maybe we could take some questions, particularly if you have questions about the project that he's worked on. Yes.
Dr. Yu, could you say something about how this project was presented and involved citizens, and how was the reaction?
Yes. Okay. Let's go to the air quality project. Okay. Our system is actually based on a framework that combines cloud with CLAN. So user can access information of real-time air quality throughout the entire city by using either a mobile client or a website here. So we have published the mobile client through Windows Phone App Store. People can install the app on their mobile phone and they check the air quality anywhere. They give us feedback about the user-friendly, whether the app is user-friendly enough or what they need, so we can improve our service. But I think what your question is not only about users, but also government, how to get them involved. It's maybe even more difficult than get a user involved. I think users are pretty much interested in this technology because they need it. We can provide benefit for them. They can inform their decision making. According to the forecast, air quality forecast, they can plan their trip, whether I can go picnic tomorrow or we should cancel my trip, whether we can do some outside activity or not. So this is influence their daily life. They like it, they check it. We have probably hundreds of thousands of users in the past 1 year. We don't do any advertisement for the mobile client, but the user is growing. But according to the experience, how to involve government inside, that's not easy. It's a painful experience, I can tell you. Again, it's a long journey. We spent about 2 years to get this project really done. We have to present this technology to different level of officials in the government. And we have to be ready to deal with the last minute requests. You have to understand what they need. Sometimes they don't really know what they need. We have to figure out what they need with them, working with them. So that's real. I think it's a general case in China. Yeah.
This is Alfred Wu. My question is a bit, I would say, a bit technical, but I'm not a specialist in data analytics or big data. But I kind of observe the big data idea is actually getting the data together, which I agree with you. It has to come from different sources. That means the fusion of the data set that come of new intelligence. But I have a doubt whether getting all the data into a single place and start to do this multidimensional data crunching is the right approach. I just wonder, in your research, do you see some people, they actually kind of distributed the data crunching approach into different so-called specific domain, and then bring the so-called have distributed intelligence in different data set, and then bring them together to come off next level intelligence? So this is like my question.
Can you summarize your question?
So my question is that my understanding of big data is actually getting the data together, right? Let's get the data together, and then they come from different sources, like your example, right? Yeah. Some of these are social, some of these are scientific, some of these from the government, right? And then let's gather the data and then start to crunch, see what might be the insight that doesn't come from a single data set. So my question is that is there anybody from your research point of view that you see other people actually trying to derive certain intelligence from the specific data set, which are specific to certain domain, and then with certain credibility, and then mix them together? So in that kind of architecture, you don't have to host everything into a single place, because some of the challenge of getting all the data in the city is challenging because of many reasons.
Yeah, so what I think what you said is a kind of data as a service. So the data can be hosted in different places, but they're open service for different application domains. Some places it is true for the text data. So you can see the text data is hosted in one places, but different application can call API or call you can pay for API to get the data. For the air quality data, meteorologic data is the same thing. Okay? They host the data in the central place, but they open API publicly for free. Then you can access the data, get data back to your applications to solve the problem. And this is real for our case. Our air quality data and meteorologic data was collected from the API provided by governments. Yeah.
Yeah, quick question on the noise prediction. How did you validate the model in terms of discrepancy with realities, that means the veracity of the prediction, and also utility, such as after that, could there be less complaints as opposed to you not use the prediction model, which is different question from accuracy?
Quite very good question. So we don't have time go into technical details, but we have two ways to evaluate how this model works. The first way is we have some data, 3-1 data in some places, which is dense, okay, good enough to represent the noise situation of this particular place. Then we can remove this part of data and then recover the data of this place by using our algorithm. Then we can measure them against the real data to see how accurate it is. This is one way. The second way is we really send out students, carry on mobile clients to check the noise situation in 72 places in Manhattan. At a different time of day, they recorded the noise level of different places. Then they come back. We can rank this location, 27 locations, in terms of noise level, relative ranking. Say, and use this ranking as a ground truth. Okay, then we use our noise indicator to rank these locations and see how these two rank are close to each other. So this was widely used by information retrieval technology. Yeah, thank you.
Yeah, just curious as to why you needed to build a model and rather than use mobile sensors. In London, we put sensors on vehicles and we get a very dense map of air pollution 24/7. We have them on the buses and so on. Sensors are cheap, and you can get an accurate measure and a very dense map of air pollution that way. Okay, good question. You mean air quality one, right? Okay, let me tell you. Actually, the sensor for measuring 2M2.5 is huge and not easily portable. For CO1 and NO2, it's easy. It's kind of gas. But for particle filter, for particles, the devices, okay, has to be big because
it has to absorb enough volume of air to calculate the density, I mean not the density, the mass of the air pollutants. Then you will be able to calculate the air pollution index. So it's very expensive. I can tell you how expensive it is. It's about, okay, let me say building a station of air quality monitoring station, okay, about 1 million RMB per station. So you know how expensive the device is. It's not easily portable, and you have to stay there for a relatively longer time, for example, 2 hours, until generating a reasonable reading. So you cannot move around. That reading is not accurate enough. You have to stay with a very, very professional device, deserving maybe 500,000 RMB, and stay there for 2 hours. I don't think people will do that for us. Yeah, so that's the reason why we don't use that. There's some solution is considering combine cheap sensor with expensive sensor. That might be a feasible and potentially enable a new way. Yeah, but right now we didn't see that's accurate enough solution. Yeah.
A quick question. Yeah, you said domain knowledge is not so important as data analytics skills, but we are saying between our colleagues that we are saying very open, data is a liar. So that means unless you understand the real meaning of each data, you must be misguided. So we always emphasize the involvement of the domain specialist in our big data analysis. So I'd like to your reason why you say that.
Okay, thank you. I said we may need less. We don't say we don't need little or we don't need the knowledge. Of course, we need the domain knowledge. For instance, when we're doing the air quality project, we have to read the literatures written by people from environmental theory. We know what they care about, what the problem is, and what kind of parameter and feature they are using in their models. So we can grab some data that could extract correlated feature, and we put data together using machine learning and the data mining algorithm. We can come up with a much more complicated or complex model that may be more accurate than classic model. The reason why they use classic model is because at that moment they only have a very little data. So we have to leverage human knowledge or empiric assumption. For example, we assume this is a Gaussian distribution, but in reality, it might not be true. Or in some specific case, it is not true. But given the data, you can train a much more sophisticated model with hundreds of parameters. You can handle different cases. And I don't think there's a conflict between classic model and machine learning model, because both of them are fitting the curve of data. Using, let's say, some classic model, the gravity model, they are fitting the data, a small portion of data, but at this moment, we have a huge number of data. At this moment, we cannot process data by human effort. So we need to leverage machine learning and algorithm model to automatically build a model, a very complicated model that we cannot write with human hand. So they are essentially the same thing, and in the future, maybe the machine learning model I learned today become classic model in the future and be replaced by another model incorporating more data source, deeper knowledge. So that's the evolving of the model, I think. Yeah.
Well, thank you, Dr. Cheng. I think we will now hand the mic over to Steve Adler, who will also talk about his experience with governments and open data.